Good afternoon, everyone. And today what we are going to do is we are going to take it one step further from where we left last time. You might recollect we had looked into four sampling designs, and we had looked into how the data looks like, provided we know where the activity centers are. How was the the histogram of distance from the activity center summing up. And we also saw how in some designs you had more animals getting trapped on a certain cameras, whereas in others it was the other way around. So let's go back to this graph, which you might remember we had briefly discussed in the second session. Essentially, it's about um, let's say, this little person with a small flashlight. He is walking on this space and he has to find the peak. Now, he doesn't have a long vision, so he can't walk straight up. He has a very short vision, so he can only look around where he is. And what he really does in this case is something like this. So he basically just goes around and starts looking at every point, which is, oops, sorry, where is the annotation? Annotate. Yeah, at each point, he looks whether the next neighboring points are higher or lower, and then keeps doing that for a long space. And then once it starts finding the altitude increasing, it keeps looking, okay, there's nothing going this side, and then ultimately sort of it quickly reaches the peak, because every point next to this one, this side, or this side, they're all lower than on the other side. So essentially it just kind of takes this quick path all the way to the top. That's what maximum likelihood is. Given the data, what are the most likely values of our unknown parameters is what we are really estimating here. In this case, in spatial capture recapture, we are trying to look at three unknowns: density, encounter rate at activity center, and ranging parameter, which is sigma. Okay. Now the next slide is what we okay, so let's go back to this one where we went to estimate the snow leopard population from Spiti. If you recollect, the snow leopard abundance here was random, which means that in any subsection of this entire study area, the density is more or less the same. Wherever you are sampling, you will end up counting more or less the same number of animals. And that's what random means. You might be a little low, a little higher on a couple of them, but if you just randomly choose 6 points, as I did here, you end up with a fairly concise estimate. And that's a true random distribution at this point in time. So for this random sampling, the first scenario, if you might remember, where we set up cameras pretty far from each other. Now, the reason we did that was because we wanted to cover the entire study area with about 56 cameras that we had. And we created a wide grid cell, and we leave it for a certain period of time to capture snow leopards. You might also remember that we discussed that this may result in several individuals getting photographed, which is great, but that the number of recaptures of snow leopards on multiple cameras may not be as high as we would want it to be. So truly speaking, the number of snow leopards which we have on camera will be pretty high, but the number of snow leopards at different distances from the potential activity center might be less. If we end up with let's say 56 snow leopards, and each snow leopard is photographed once or 5 times on a single camera, that's not enough information, because it may somewhere mean that the activity range is this much, but then the solver may not have enough data to be able to say where the actual center is. So, and if you really, there are times you do end up in a situation like this where you have a lot of cameras and you have many pictures of snow leopards on the same camera, but not on any other cameras. In those situations, the analysis can be, well, technically it really refuses, it complains to run the analysis, complaining that you don't have enough, you don't have any animal which has been recaptured on more than one unit. So that's where the analysis stops, and you have to go back, redesign your study if need be, because this is not going to be able to do justice to our expected outcomes. So in other words, what we are doing is, in this scenario, we're not giving snow leopards enough cameras to get their selfies taken on. We're giving each snow leopard one camera, maybe less than one camera in some cases. In case there is a snow leopard whose range is somewhere between this, then we might be giving it less than one camera to get photographed on. And that's why we do end up with a situation where we may have few snow leopards on, quite a few snow leopards on camera, but maybe the data may not be that good. Now, this is how the typical capture data looks like. You remember we had discussed that each snow leopard is getting captured on one camera trap or more. Now here, if you look at it, I would suggest you ignore these two lines. Just look at ID and trap ID. ID is the name of the snow leopard. So there were 50 snow leopards in this population. So the snow leopard number 2 has got captured 3 times on camera number 15. Snow leopard number 3 has gotten captured 4 times on camera number C37. Number 5 has got captured only once on 23. Number 6 has gotten captured on C40. This is just a small cross section of the whole data. 2 might have also gotten captured in some other camera further down. We don't see it here, but you can, when you see the data set, you will be able to observe those differences, those details. Here, C15 has captured snow leopard 9 as well. Now, in other words, what this looks like is something that you can see here, like this. So you basically have C15 having captured 2 different snow leopards, snow leopard number 2 and snow leopard number 9. Similarly, C23 camera, at least what we are seeing right now in front of us, has captured snow leopard, which is named 5, and so on. So what you're essentially seeing here is, on the left-hand side, this is the capture data, which really defines the name of the snow leopards that you're giving them, and on which camera this particular snow leopard has gotten captured on. That's all that it is showing. On the right-hand side, what you're seeing is, you're seeing the coordinates of the camera traps. In other words, the way these two data sets are connected are this trap ID. Trap ID is common between the two, and what it's doing is it's connecting the two data sets. So if you have hundreds of encounters here, each of those encounters should be listed or should be on one of these cameras. If you end up in a situation where your, say, one snow leopard has gotten captured on a camera which is say Ranger 20, and that Ranger 20 is not listed here, then the software will complain that you have one snow leopard, or you have some individuals which have been captured on traps that are not listed. So there is no spatial information about those snow leopards. You may end up with situation where several cameras may have no snow leopards captured on, and that's fine. So you will have, let's say, out of 56 traps, only 30 cameras have had snow leopard encounters. That's a perfectly normal situation, which is what you might end up with. But to have a snow leopard captured on captured and that camera not listed in the trap data is not not practically, technically it's impossible to happen. So that's why you have to be careful that each of your camera listed here should also have a coordinate mentioned here, and make sure the spellings are exactly the same, no spaces, no differences in caps and otherwise as well. No dashes or hyphens or dots, which if you want to use them, then use them on both. If you don't want to use them, then don't use them on both. So there should be a uniformity in the naming as well, because this is the only variable which will help the two data sets talk to each other. Okay, so moving on, this we've done. Now, what we do is to analyze Snow Leopard camera trapping data, we would strongly recommend that you use R. There are many Windows-based software, which are more like graphical user interface based software, which seem to be very convenient to use. But the problem is many of them are quite limited in their flexibility that they provide. And R is a free programming tool that can be downloaded from these links that you can see here. It's perhaps one of the most popular data analysis and programming tool that's being used today. I think the other one is Python, and then C, and other ones which are more technical. But actually, all the graphs, visualization, and map that you've seen or will see in this course are all developed on R. And what we will be able to do is we will be able to give you the entire script along with the source code and the data sets that we have generated to be able to do it yourself. So the replicability is one of the best parts of using R, because you can, every step you can do it. You don't have to memorize which step should come after which one. Once you have done a certain workflow, that workflow gets recorded, and you can always replicate the same workflow whenever needed. So if you're well versed with R, that's wonderful. If not, I think you can still run some of the spatial capture recapture analysis, because they're very simple workflows available here. But we will still very strongly encourage you to take some basic courses in R, not to just learn this programming tool or this analytical tool, but also to not get intimidated by command lines, because once you start using these, you'll realize they become your assistants, because you don't have to memorize anything anymore. You just have to follow a workflow, which is almost like step 1, step 2, step 3, and so on. So many of you may have already used R, but those of you who haven't, or those of you who have, just a quick kind of a recap of how R works. We use R Studio, which is actually one of the workspace tools available to use R. And the reason we use this is because it allows a lot of work to be saved, and makes a lot of our work reusable at a later point in time. Now, we use R Studio because it allows several conveniences as well. You can visualize data much more easily as opposed to working directly in base R. Anyway, you can. So this is how it looks like. You can decide to keep which windows to show on your screen and which one you would like to hide. But the first one is called the source panel, where you type in your codes. Your codes don't get run until you use Control Enter or press this little button here which says run. The environment and history panel is that's the environment and history panel, which is where you review the objects that are there in your workspace. You can view tables and other variables in a very graphical user interface in this little panel. The console over here is where you see your outputs. You can also directly punch some code here. For example, I just need to find out what is 5,320 plus 231. Rather than opening a calculator, I can just type that there, and it will immediately tell us that estimate. And lastly, this panel, which shows plots, packages, help, and other functionalities. So this is typically how our Studio Workspace looks like. When I'm not saying use this one, but this is what we've been using, and we find it pretty efficient to use for various reasons, as I just mentioned. Now, while we may need several functionalities during any analysis in R, for this particular analysis using Spatial Capture Recapture, we will only be using this one package, which is called SECR. Once you are in that console, in this little, in this, what is it called? I keep forgetting. The source panel. And once you're in the main window in the source panel, you can enter the following code. You say install packages and give this name. It automatically connects to internet and downloads this package if you don't already have it installed. Once you have downloaded it and installed it, by just clicking the line above, you click on you type the function, the command which says library and SECR. This loads all the functions that developers have created to run this specific analysis, which uses maximum likelihood to estimate snow leopard density, or to estimate wildlife density using spatial capture recapture. Please note that we are using SECR for the diverse range of analytical flexibility that it offers, but there are other equally useful tools, such as I think one is called OSCR. Then there are people who would like to use not maximum likelihood based approach, but Bayesian approach, and they can use other tools like JAGS and so on. So there are various means you can deploy to run spatial capture recapture analysis. We are using SECR package for its versatility and the uniformity of the logics that has followed from the publications by David Borchers and Murray Efford. The only reason, personally, I don't use Bayesian approach, even though it has some benefits over maximum likelihood, is because it takes a long time. One analysis, if I'm not mistaken, can take anywhere between 25 to maybe 100 times longer. So while one analysis might be done in 10 seconds, the other might take several minutes, and then longer analysis can be much slower. Right, now this is just a quick update, and this is something that I had had missed out earlier. You can have many types of traps to run spatial capture recapture analysis. One can use physical traps where animals are once they're trapped, you have to take them out, tag them, or identify them, and then release them. So once a animal has been trapped, it has to wait for another occasion for another animal to be trapped. You can use transects where you're walking and you're trapping animals through their feces and their corresponding genetic data. You can do polygon searches in small circles or squares or whatever polygon shape of your interest to look for a certain feces, for example, again, to run genetic analysis. If you have telemetry data, what's fascinating is that spatial capture recapture analysis can take telemetry data to improve inference and to even estimate abundance based on the known number of individuals that you have and their movement parameters. So you can input telemetry data as well, or as we are using here, we are using camera traps, which are typically known as either proximity sensors or count sensors. We'll talk about these two a little bit today. But again, we won't be having the time to go through all these different sensor types, but just know, and there is a lot of literature available even on the web, on the net about these different types of traps that can be used. And there are e-groups where people have been discussing their approaches and analysis using various trap types as well. So quickly going back to our first data set from the large study area, from the large trapping grid. Now, this is how the data looks like. And we have named the two files as large.cap and large.trap. How do you define them? It's a very, so if you have a capture file where, with this file, if you have it as a CSV or an Excel file, you can simply read it on R through this read.csv command. The trap needs to be created with a little bit of a process here because traps have several properties that are looked into. But once you have read a trap file, you can read a trap with a file that looks like this, where this is the row, these are the row names, these are the column names, and so on. And this is where you define the detector type as being count detector type, because the reason being camera traps don't stop after taking pictures. They keep taking pictures for as many number of hours or days or weeks that you set them out for. In other words, camera trap is able to count how many times an animal is moving in front of it. That's why we call camera traps as count data type, count type traps or count type detectors. Right, and also the other factor being that a camera trap does not restrain an animal to become impossible for those animals to be captured again. So in earlier times where you had camera traps that would just take one picture and stop, that's when you would have a certain kind of capped trap, if we may call it. But in this case, camera traps operate for several days at length, and that's why we call them as a count detector. So once we have the data like from here, what we do is we give a particular function or a command to the R programming on the R console, and we tell it to make capture history. The command is called make.capthist, and all you're telling it is that for captures, please look at the large.cap data that I have imported. For traps, please look at the large trap data that I have imported. And my formatting of the data is in the format of trap ID. Again, there are many formats in which you can organize your data. We have been using this trap ID formatting just because we feel it's among the fastest when it comes to the analysis. So that's the only reason. And but then again, our data types have the flexibility to be used as trap data or XY data as well. But just because it's more convenient, we are using the trap ID format. So the format that I just showed you 2 slides before is the trap ID format. And the moment we do that, it'll just go, the moment you enter the, press Control and enter on this command, it will create a file. It won't give, if it gives an error, that means you have to fix something. If it doesn't give any error, that means your data is loaded. Now you have a capture history data which has information about traps and capture multiple captures of individuals to be used for an analysis. So this is only half the job done. You might recollect that there are 3 types of data sets that go into spatial capture recapture analysis: the locations of captures, the locations of traps, the locations of or the actual capture data where we know different individuals getting trapped on different camera traps. And the third one is the integration space, the extent of an area across which the software should integrate the likelihood. And to talk about that part, I will pass on the baton to Justine. She'll take you to help understand some of the very important nuances of masks, because that's something which can have a huge implication on how your analysis can go. So Justine, over to you from here, please.